The second part of the lesson on tangency problems is about parametric curves. What is a parametric curve? A parametric curve is a kind of curve given by two or more functions that share the same parameter. Here's an example. X is given by this function of t, and y is given by this function of t. Let's take a look at this curve through this mathematical program I wrote. Here it is. The parametric curve given by the function that we saw before. The best way to understand the parametric curve is through a moving particle model like this. Here, the red dot represents a moving particle. X of t and y of t stand for the horizontal and vertical components of this moving particle. Horizontal and vertical components of the position of the moving particle, excuse me. The student with some physics background must have seen this kind of example. And the derivative, that is x prime of t and y prime of t, represent the horizontal and vertical components of the velocity of this moving particle. Let's take a look at another example. Again, we have a function of t and function of t again. And then let's run this mathematical program I wrote. And here's a visualization. Again, the moving particle model given by this red dot. X of t and y of t stand for the position of this moving particle. Here, please do not pay too much attention to this gray arrow because this program was originally written for polar coordinate, so it is showing the polar direction. Here, the red dot and moving particle model will suffice. The reason we had closed curve for those examples is because both of these curves are given in terms of sines and cosines only. Sines and cosines, as we know, are periodic functions. Consequently, we have closed curves. We'll see some examples later on, the parametric curves that are not closed. If we have three functions like these, then we're going to have a 3D curve. A little bit more complicated to visualize, so let's stick to the easier cases. Now let's go over to example problems, the kind of problems that deal with tangency of parametric curve. The typical problems are like this. A parametric curve is given by x equals to x of t, y equals to y of t, and time t is fixed with t naught. In that case, you have to find out a point, x naught and y naught, by plugging in t equals to t naught to those functions. And then we have to find out the derivative, x prime and y prime respectively. Finally, the slope formula. Slope turns out to be y prime of t naught over x prime of t naught. Let's talk about why that is the case after dealing with at least one example. Now that we found out the slope in step 3, an x-coordinate and a y-coordinate in step 1, we can put everything together in slope point equation of that line. Breaking off the parentheses and then simplifying, we're going to get a slope-intercept equation. There are some exceptional cases though. What if slope doesn't exist? For example, denominator is 0 in this case. Then m cannot be defined. Now what kind of line has no slope? It's going to be a vertical line. So an exceptional case, x equals to x naught, could be an answer. Now, let's go over to at least one example, and then let's find some time to talk about why the slope formula take place. Let's go over to problem D. It's a little bit complicated, but I believe we can handle it. Let's go. Step 1. We have to find out x naught and y naught. All we have to do is plug in given t naught value, pi over 6, to the function. So if we do that, 2 times pi over 6, 4 times sine of 2 times pi over 6, so sine of pi over 3, minus 2 square root of 3. Turns out sine of pi over 3 is square root of 3 over 2, so 4 times that is 2 square root of 3, so these two cancel each other out. We have just pi over 3. The problem was designed to be simple like this. In this case, well, after a little bit of simplification, cosine of 5 pi over 6 turns out to be negative square root of 3 over 2. So again, this part cancels out. We have pi over 6. Alright, step 1 is done. X naught, y naught is done. Let's find out the derivatives in step 2. Calculating the derivative using the chain rule, this is what we get. The derivative of 2t is just 2. That was easy. Sine becomes cosine. And don't forget the chain rule. The derivative of inside is multiplied times 2. Simplifying, we're going to get 2 plus 8 cosine of 2t. We can do the same thing to the other function. Derivative of t is just 1. And derivative of cosine is negative sine. Don't forget the chain rule. Derivative of 5t, we have to multiply 5. Simplifying, we get 1 minus 10 sine of 5t. So we got the derivatives. What we need now, we want to find out the slope. Y prime of t naught over x prime of t naught. Let's calculate that. Here we go. Y prime of pi over 6. X prime over pi over 6. So this one, when t equals to pi over 6, we have numerator and denominator. That one, okay. And computation is rather simple. We get negative 4 over 6. We have negative 2/3. That's the slope. Step 3 is done. So step 4, we know the slope, we know the x coordinate, we know the y coordinate. So all we have to do is put everything into slope point equation. Here it is. Negative 2/3 times x minus x naught plus y naught. Now, this is perfectly correct equation of a tangent line. However, you have to find out the slope-intercept equation. So let's do a little bit more algebraic manipulation. Break up the parentheses. Negative, negative becomes plus. And then take the common denominators and put them together. We're going to end up with this final form of the answer. Negative 2/3 x plus 7 pi over 18. This concludes the solution of the problem. Now that we are done with the problem, let's verify our solution through Mathematica program. Please note that we have the same functions defined here, and t naught is pi over 6 given. Alright, let's run this program, and what do we have? We have a parametric curve like this, and then we have a point. That's when t equals to t naught pi over 6, and then equation of the tangent line at this particular point, negative 3/2 x plus 7 pi over 18 is indeed a tangent line. We can see that over here. Also, this is an example of a curve that is not closed. Of course, overwhelming majority is not closed. There's no surprise here. Sine and cosine may be periodic, but these are not periodic. Alright, let's finally talk about the theoretical background behind the slope formula. Here is the visualization through Mathematica. Oh, excuse me, that was unnecessary. Here we go. This is the case for a graph of a function. Y equals to f of x is given. Here's a point of interest. What we do, we take the second reference point and then find out the slope of the secant line. The delta y over delta x, the difference of y coordinate over difference x coordinate, turns out to be the slope of the secant line, rise over run. And as we move the second reference point closer and closer and closer to first, the secant line will approach the tangent line, and delta y over delta x will approach dy over dx, the infinitesimal case, or 0 over 0 type limit. That is the derivative concept. Here we're going to do the same thing with parametric curve. Here's an example of parametric curve. And let's suppose we have an interesting point here, and we take second reference point over there. And we're going to have difference of y coordinate over difference of x coordinate, delta y over delta x there. And as we move the second reference point closer and closer and closer to first, this secant line will get closer and closer and closer to tangent line, which will look kind of like this way. And what kind of limit do we have? Rise over run, delta y over delta x will approach the infinitesimal case, dy over dx, the slope. But y may not be a function of x directly, at least in the extended interval, so we use the chain rule. Dy over dx can be expressed as dy dt over dx dt. And what is dy dt? It's y prime. What is dx dt? That's x prime. Evaluating those at t equals to t naught, we're going to get the slope. So that was a quick derivation of the slope formula. Let's review the step-by-step process just once more before concluding. Step 1, we find a point. When time is fixed, we're going to get x coordinate and y coordinate of the position. Next, we find the derivatives. How fast horizontal component is moving, how fast vertical component is changing. We have two rate of changes: horizontal velocity, vertical velocity. And step 3 is a slope formula. How the slope of the tangent line is related to rate of changes. And we saw this in this picture and the chain rule. Finally, if we have slope and x coordinate and y coordinate, we're going to have slope point equation of the line. Exceptional case, when the slope is undefined, we're going to have a vertical line.